All right, this week we'll focus on tropical weather. So we've moved from extratropical, mid latitude, global scale. Now we're going into the tropics. Uh, every once in a while, tropical weather does come up and bother us. There have actually been the remnants of tropical systems that have made it into West Virginia, uh, different areas of the eastern part of the United States, even into Chicago area has had remnants of tropical systems. So tropical weather, while they may form in the tropics, can impact all of the United States at some point. So, what are the conditions for the development of a tropical cyclone? Well, almost what we consider tropics is basically between the Tropic of Capricorn and the Tropic of Cancer, 23.5 degrees north, 23.5 degrees south. In this area, fronts don't pass, so there's not a lot of temperature variation, and the diurnal temperatures don't really vary a whole lot. There might actually be more variation in diurnal temperatures, though, compared to the monthly means. So basically, it's a uniform air mass. In the tropics, thunderstorms do develop. They develop from the intertropical convergence zone. Sometimes there are minor disturbances in the atmosphere that trigger them, and they even kind of look like mid-latitude squall lines. One of the interesting things about the analysis that's done in the tropics, instead of using isobars, we use streamline analysis. What we're doing is, if you look at the wind barbs, we just start drawing, as a meteorologist, drawing lines that flow with the wind. So you connect wind barb to wind barb and just trying to keep the lines going. And that will actually show you areas of convergence and divergence much better than the isobars will. But it's really useful in the tropics. Not exactly a lot of use up in further north, even though it does sometimes come in handy. So a hurricane is very intense tropical cyclone, greater than 74-mile-per-hour winds. Oh yeah, contrast this. Where we talked about extratropical cyclones, hurricanes originate in uniform, warm, humid air mass. There are no temperatures differences across that air mass, and hopefully, really not much in the way of moisture differences. Sea level pressure is lower a lot. And horizontal pressure gradient is extremely intense, very tight, especially in the near the eye. So a hurricane is also a much smaller system, where extratropical systems may cover 1,000 miles or more. A hurricane may only be 100 to 200 miles across sometimes. And the other thing is, it's a warm core system. What does that mean? Well, think about it. We know that warm air is less dense. So as you're going up in the circulation is weakening. Pressure doesn't drop as fast in the vertical. So you actually wind up with an anticyclone on the top of a hurricane. You're not going to get that with an extratropical system. Here you can see the eye, beautiful image, and the stadium effect of an eye wall in a Hurricane Hunter aircraft. When you look at a hurricane, there are various rows of clouds around the hurricane called spiral bands. So these bands each have convection, showers or thunderstorm type convection. The closer and closer you get to the eye wall, the more intense those showers or thunderstorms are. And all that wind that goes up in the eye wall has to come down somewhere. Where does it go down? In the eye. That's why the eye is clear. So now that we've looked at the typical structure, oh yeah, there's an anticyclone on top, which actually helps the air to literally have like a chimney effect, pulling it out very quickly. Some of the necessary conditions, you got to have relatively warm sea surface temperatures, basically above 80 degrees. There must be some Coriolis force. In other words, you're not going to get this if you're down by the equator. Oh yeah, and you want weak winds aloft and a pretty humid air mass. So if there's a lot of dry air floating around, you're not going to get the convection developing and doing its thing. So here you can just see a picture of how warm the water gets sometimes. There is the Gulf Stream off the east coast of the United States, and that has temperatures, in this case, well up above 76, 80 degrees even. at this time. Uh, Sometimes you get little eddies in it. And down in the Gulf of Mexico, where the Gulf Stream originates, you wind up with very hot, humid water, humid water, very hot air over the water there. That temperatures get into the 90s in the water temperatures there. Why do you need that Coriolis effect? Because without it, you can't get a circulation of wind. Weak winds aloft allows the thunderstorms to organize. So during El Nino, usually the winds are strong aloft. So that's why during El Nino, hurricanes are less frequent. Here is where and when. One of your questions is going to talk about the differences between the Pacific and the Atlantic. When you look at the Pacific Ocean, it actually is more active than the Atlantic Ocean. On average, there are 25 storms there and 16 become typhoons. But the one thing is, none of them almost ever are going to reach the United States. Remember, we have an easterly flow down there. So the storms that form off of Mexico or in that area around Baja are going to tend to move towards the west away from the U.S. However, over the Atlantic, where there might be a little less storms, they are going to have a better chance of hitting the United States. Here you can see where they typically develop. And you can see that the prime time is late August through September, basically. They start going down after that. But the only months of the year we've never had hurricanes are January and February and March. And even, I guess, April as well. I believe there's been one in April. But you can see here, the rest of the year, there are hurricanes out there. And you can see how they change. Hurricanes tend to develop where the water gets warmest quickest, so the water needs to be shallow. And the Gulf of Mexico is actually a relatively shallow water. And then they begin to move out over the Atlantic as more and more disturbances come off the Atlantic, off the Sahara and Africa continent, and eventually move up the East Coast there. So basically, you get an easterly wave or some kind of tropical system. An easterly wave is just a low pressure system in the tropics. And not a lot of these actually develop into hurricanes. A very small percentage, because usually there might be wind shear, maybe some dry layer. One of the things, Sahara air layer, we actually had it in the news. It's basically a very dusty, dry air mass, very stable, kind of inhibits convection. It also has some pretty good wind shear with it. So everything it does takes away from the potential for thunderstorms. One of the things you need for a hurricane is you need a lot of water vapor to condense, releases latent heat. Heat of the air rises. A lot of cooling aloft as that condensation takes place then. Rising temperatures in the storm's core and divergence of air aloft. And here are the basic categories. Tropical depression, you have a circulation with 23 miles per hour or higher wind. 39 mile an hour or higher will get you a tropical storm, and 74 will get you a hurricane. And they can go up and down in this classification, as we saw all year. One of the things, too, is most of the deaths of hurricanes occur from water, either from storm surge or rain. Over 75% of them are in that category. The other ones are much less significant. Even though they can have deaths, it's the water that's the most dangerous. And here you can see how water inland flooding Port Arthur, Texas, with rain from it. Tremendous rain from Harvey, Amelia. Over 30 some inches, over 50 some inches actually, are the maximum areas here, right along Houston area. So that area just got clobbered with rain. The winds are caused by pressure gradient force. Debris transported by the winds increases the damage. And there could even be some whirlwinds right around the immediate center. Winds will diminish very rapidly upon landfall. One of the things is, remember that over the ocean, there's very little friction. As soon as they hit land, they're getting friction. So those winds are going to begin to slow down. And it's lost the ocean heating. So all that wonderful moisture that it's had to keep it going is gone once it hits land. So that, again, is going to allow this storm to begin to weaken. But once they hit landfall, storms do tend to produce tornadoes. Think about it. There's all these bands of showers or almost thunderstorms all around a hurricane. The low level wind weakens. As soon as it weakens, the upper level wind is not as fast to respond. You get very strong wind shear, like you would in any thunderstorm that produces tornadoes. So hurricanes can be a very active environment for producing EF0, EF1, even EF2 tornadoes. And usually you're going to storm on the northeast or east side because most of the hurricanes are moving to the north. They're always going to be on the right side of motion of the hurricane where the tornadoes form. Storm surge, it's just a dome, wind-driven dome of water. And what that basically means is the more wind you have and the bigger area the winds cover, the higher the storm surge can be. If you have a very small storm, maybe you'll have an intense storm surge in a very small area. But you're going to be doing a paper on Sandy, and Sandy had 1,000 miles of wind with it. Think about all the area it had to pull over the water into bringing in that water into the land. So even though it wasn't as strong, it produced a much greater storm surge because it had a huge area of wind. So here is basically what happens. The sea level rises. So where the mean sea level might have been down here, way below this house, if you have 15 feet of storm surge, maybe all of a sudden the sea level is up here. So now the waves on these wind storms and everything are coming in and hitting your house. So that is what basically happens with storm surge. You can actually see the destruction here. Notice all these nice houses sitting here, not there anymore, all because of that storm surge that clobbered that area. So there are different models to predict storm surge. I actually did some research in that area with some different universities and stuff. The SSTs have been relatively warm lately, so that's helped to continue our trend of higher than normal hurricanes. You can see they run in cycles. The Atlantic multi-decadal oscillation. Look at the 1920s through the 1960s. Almost all that time, temperatures were a little bit above normal. Well, starting in about late 1990s, we've been running the same thing. So we have another maybe 10 to 15 years of this cycle. And if you add in global warming, maybe it'll even be more interesting that way. So these warm cycles are interspersed in here and cause the thunderstorms. Notice in the 60s and 70s that water was colder. You didn't have much in the way of hurricane activity. It gave people a false sense of security. They went to the ocean. They liked it there, so they settled there. El Nino could definitely have an influence on it. When it gets El Nino, wind shear gets stronger over the Atlantic, causes some problems for the hurricanes to develop. Here is an estimate from the World Meteorological Task Force that if you change the temperatures by 2 degrees, obviously storm surge is going to go up because you're raising the sea level. Tropical cyclones will have more rainfall, again, because hotter air can hold more moisture. And the intensity will increase, but not necessarily the number. There'll be a greater proportion of tropical cyclones that reach 4 to 5. And hurricane threat to the southeast of U.S., big time trouble there. Barrier islands are a great way to protect them. Think about the Outer Banks. In Virginia Beach, we have Sand Bridge that actually blocks part of the waves from the Atlantic from coming to the main part of Virginia Beach. So there are evacuations routes all over the southeastern U.S. There are different ways of mitigating the loss. One may be preservation of such things as mangrove swamps, maybe eliminating building in certain areas, or designing buildings that they withstand floodwaters better. And every year, Colorado State University started it, and now a lot of other people do it, including the National Hurricane Center and all, issue year-long forecasts. There's something called the accumulated energy index too. Basically, it takes into account how strong the storms are throughout the year. And the higher this number is, means you have more storms and more intense storms. They tried to modify it one time, hurricanes. It just didn't work. Never were able to do it right. One thing I wanted to show you quickly is, say you even wondered about it now, temperatures are still down in this area above 80 degrees. So technically, a hurricane still could develop down here. Now, once they got up here, they're going to be dying. But they are possible. I just wanted to show you, I found this image of all that were out there one time this year. And you can see them all over the place here. Hurricane, tropical storms, so many at one moment in time looking across the globe. And this happens every year to a lesser extent. This is about as big as will ever see. So hope you got something out of this lesson. One thing is, just keep in mind, tropical systems are not the same as extratropical systems. However, at the end of it, as a tropical system is moving into the United States and moving further north, temperature contrast could develop at that point, and it will transition from tropical to extratropical. That actually happened with Hurricane Sandy, which you will be writing about. So remember that.